Hello, my name is Thomas de Boer, and today I'll be presenting my poster titled Characterizing Anisotropy within the Montney Formation. To provide some background, the Montney Formation is a substantial geological unit with significant hydrocarbon potential, and it spans approximately 130,000 kilometers across northern British Columbia and Alberta in the country of Canada. The Montney Formation is dominated by a siltstone lithology, and it's emerged as a focal point for hydrocarbon exploration and production due to the recent implementation of hydraulic fracturing techniques. These techniques have revolutionized the extraction of natural gas from unconventional reservoirs such as the Montney, as their reserves were previously deemed uneconomical for development. Hydraulic fracturing involves a high-pressure injection of fluid into the rock formation, which creates artificial fracture networks which enhance the permeability and facilitate the extraction of hydrocarbons which are locked within the rock matrix. These are also known as tight reservoirs. Despite this increase in fracturing activity, there remains a significant lack of data related to the mechanical properties of the Montney Formation, both within existing literature and within the industry. A pivotal factor in the behavior of hydraulic fracturing is the anisotropic properties of the rock, that is, the directional variability of the physical properties of the rock matrix. Anisotropy plays an instrumental role in influencing the initiation, propagation, complexity, and direction of fractures resulting from stimulation of the reservoir rock. This directly impacts the production capabilities of a particular well which has been hydraulically fractured. The shales and siltstones that the Montney is comprised of are both highly heterogeneous and anisotropic. The geomechanical properties of the rock vary with bedding orientation, thickness of those beds, the material that those beds are made out of, and the distribution of these beds relative to each other. The aim of this study is to characterize the response during unconfined compressive strength testing as the angle of the bedding is changed with respect to the applied load direction. The UCS testing provides a foundation for the understanding of how anisotropic rock influences fracture development. For the methodology, large rock blocks were obtained from the Kamenka Quarry located in Harvey Heights, Alberta, where there is an outcrop which is considered to be the equivalent of the Montney Formation at depth. Samples were cored from these blocks from 0 to 90 degrees at 10-degree increments, with a minimum of 3 samples being cored at each orientation. Following the extraction of the samples, they were prepared and tested according to ASTM's UCS testing guidelines. The prepared samples were subjected to UCS testing within a specialized load frame, with the applied load and the corresponding vertical displacement being recorded. In addition to that, details on the deformation patterns, fracture initiation, and strain on the surface of the samples were recorded using a technique called digital image correlation. Digital image correlation works by taking 2 photos of the sample from 2 different angles multiple times during the testing. The sample is first treated with spray paint to create a speckled surface, and DIC software is able to track that speckled surface and track the displacement of that surface over time. Once the displacement can be tracked, you're able to, in post, calculate the strain across the sample surface. After the testing was completed, the UCS results were compiled, and the shear and normal stress components along each of the bedding planes for each orientation were calculated. The results of the UCS testing show an atypical curve when compared to other anisotropic rocks found in literature, as you might expect to see a shoulder curve where the peak strengths are at 0 or 90 degrees. Instead, we see that the peak strength is actually around 60 degrees. In addition to this, the mechanical strength of the Montney Formation rocks range from 150 to 360 MPa, which is considered quite high for shales and siltstones. By analyzing the failed samples, 4 primary failure patterns or modes were observed across the various angles, and these are attempted to be explained due to different failure mechanisms, with justifications including the fracture patterns as well as the DIC data. The first failure mode discussed is axial splitting along the bedding planes, which occurs in the 0 to 10 degree samples. If we look at the failure modes in these samples, we can see that fractures occur vertically along the bedding planes and parallel to these beds. The beds can be thought of as acting as columns, where the shear movement of these columns is confined at each end. If we take a look at the DIC data, we can see that there is a concentration of lateral strain in relatively darker layers, which are considered to be less stiff, compared to the relatively lighter layers, which are considered to be stiffer. If we look at where the fractures in this example propagate, we can see that at the boundary between a relatively stiff and a relatively lower stiffness layer, the fractures occur at this boundary. This indicates that the buckling of these layers and the difference in buckling between the lower stiffness and higher stiffness layers initiates fracture when the cohesion between these layers is overcome by the buckling force pulling or delaminating these layers from each other. Next, we'll talk about shear failure along bedding, which occurs in the 20, 30, and 40 degree samples. We can see that failure in these samples occurs as shear along bedding plane interfaces. When looking at the DIC data, we can see that there is a difference in strain, and thus a difference in stiffness, across a boundary between a relatively lighter layer and a relatively darker layer. We can see that the difference in stiffness results in a strain concentration across this boundary, which is where the fracture occurs. And we can see that this fracture occurs as a planar feature when the shear strength of that interface between the stiff and the less stiff layer is overcome. Next, we'll talk about axial splitting through planes, which occurs in the 70, 80, and 90 degree samples. When we take a look at the failure mode, we can see that most of the fractures occur vertically, perpendicular to the bedding planes. However, if we take a look at the DIC recording, we can see that failure actually initiates at the interface between the layers. If we think of these samples as a stack of layers with different stiffnesses, we can imagine that as the sample is compressed, layers with relatively lower stiffness will expand laterally more than layers with a relatively higher stiffness. This leads to the buildup of a shear force along layer interfaces, with the high normal force restricting the shear force. Eventually, as the load is increased, the shear force between these layers will be overcome the shear strength of the layer interface, and the rapid release of stress will allow vertical fractures to propagate throughout the sample, even though the fracture was initiated parallel to the layer. The final failure mode that we'll talk about today is multiple fracture or disintegration, which occurs in the 50 to 60 degree samples. This failure mode is primarily through multiple fracturing or disintegration, in which the sample explodes upon failure into a few larger pieces and many smaller pieces. If we look at the DIC data, we can see that there are distinct lines which occur not only parallel to the bedding planes, but also perpendicular to the bedding planes, and these can be thought of as dividing the sample into several subsections. In the diagram shown in the center, blue depicts the driving wedge, which extends from the top left of the sample, following along the bedding planes towards the edge of the sample. The driving wedge acts to redistribute the applied force as a normal force upon the sample's core, as well as a shear force along this bedding plane interface. Green depicts the sample's core, which acts like a smaller subsample which is loaded by the driving wedges and confined by, as shown in red, the confining wedges. The confining wedges are also loaded by the driving wedge, but notably have a much larger free surface, and these act to resist the lateral expansion of the sample's core, providing confinement. In addition to this, there is a strain concentration at the boundary between the confining wedge and the sample's core, partly driven by the expansion of the core, but also partly driven by shear, which is promoted along this boundary. The additional confinement to the sample's core provided by the confining wedges is thought to help explain the unexpected peak of UCS at 60 degrees. These confining wedges help redistribute the applied normal force of the driving wedge, preventing shear failure along the boundary between the driving wedge and the sample's core. Instead, shear is allowed to build up through the beds at the boundary between the confining wedge and the sample's core. This is reflected in the DIC data as a pattern of strain occurring between the confining wedge and the sample core, as well as in the fractures of the failed samples in which the disintegration is primarily experienced in the confining wedge as a blowout of the sample core, while the driving wedge in the sample core are generally retained as a few large pieces. The aim of this study was to help characterize anisotropy within the Montney Formation and was expected to give results similar to other anisotropic rocks in literature. Despite this, there were some interesting findings, such that the Montney is particularly strong, at least in the samples that were tested here, and there are some unexpected behaviors based on the orientation of the samples. More research work can be done here, including additional testing of more samples, as well as modeling of these samples to try to predict the fracture behavior and to better explain what is going on. I'd like to thank you for listening to my presentation today, and please do not hesitate to follow up with me or Professor Griselli if you have any additional questions. Thank you.